Hello, friends. Today, we are going on an unusual journey, where the usual flow of time loses all meaning. Imagine that you are lying on the soft, ancient earth, and above you is a boundless, star-studded sky stretching into infinity. We humans are accustomed to perceiving mountains as something eternal, unshakable, as symbols of immutability in our rapidly changing world. They stand there, majestic and silent, seeming frozen in time, like giant sleeping guards, silent witnesses of the millennia rushing past. Their sharp peaks, deep gorges, gentle slopes, all this seems to us unchanging, not subject to the flow of eras. But this is only an illusion, only a fleeting moment in the grandiose, endless dance of our planet. In fact, mountains are not static monoliths, not just frozen blocks of stone. They are living, breathing creations, the result of colossal, almost incomprehensible processes that unfolded over billions of years, long before the advent of man, long before the advent of life as we know it. Allow yourself to relax. Let go of the hustle and bustle of the day, all the thoughts and worries that might bother you. Simply breathe deeply and slowly, allowing each inhalation and exhalation to carry away tension. Imagine your consciousness becoming light, like a weightless cloud that slowly, serenely floats above the highest, most ancient peaks of the world. We will travel not through space as on an ordinary trip, but through deep time, where minutes stretch into geological eras, and human lives, with all their achievements and experiences, seem like fleeting flashes, barely noticeable sparks in the vastness of eternity. This journey does not require any effort from you, only quiet, contemplative attention. There is no need to remember anything, analyze, or search for answers. Instead, we will slowly, smoothly immerse ourselves in the flow of geological history, feeling its measured, lulling movement, like a cradle that gently rocks you. Every mountain, every valley, every hill that we see, even those hidden beneath the oceans or the ice sheets, hold the secrets of millions, even hundreds millions of years. They are a veritable record of the earth frozen in stone. But in reality, they are still changing, though so slowly that our eyes and our short life cycles are unable to detect these tremendous changes. We will speak of the gigantic forces that are at work deep beneath the surface of our planet, forces that can lift entire continents, crush solid rock like thin paper, create colossal mountain ranges out of nothing, and then slowly, patiently destroy them, returning the material back into the great cycle, preparing the ground for new births, for new geological dreams. It is like an endless, majestic dream of the planet, where the mountains are its most grandiose dreams, its wildest dreams, embodied in stone, ice, and time. Let this narrative gently envelop you, like the warmest and coziest blanket on a cold night. The words will flow slowly, measuredly, giving you the opportunity to completely relax, let go of all thoughts, and just listen. There is no need to memorize anything or try to analyze complex information. Just listen and allow the images that will arise in your mind to gently appear and then just as gently disappear without lingering. This is not a story about dry scientific facts, although they are at the heart of it, but about feelings, a sense of limitless time, a sense of the immense force that moves our planet, and a deep peace that can be found in the awareness of the grandeur and harmony of our Earth. Let this ancient wisdom of the mountains, their serenity and their patience lull you, lead you away from the worries of the day. Prepare to dive into the deepest and most peaceful geological sleep. Your journey has just begun. We begin our journey right now. Imagine our planet not as a solid, homogeneous stone, but as a complex, multi-layered structure, like a giant fruit or even a living organism, each shell of which hides its unique secrets and performs its own important function. At the very center of the Earth, in its core, lies the core. This is the deepest and perhaps the most mysterious part of our planet, divided into two main areas. The inner core is a hot but surprisingly hard ball, consisting mainly of iron and nickel. Its size is comparable to the size of our moon. Incredible conditions reign here. The temperature exceeds the temperature of the surface of the sun, reaching 6,000 degrees Celsius, and the pressure is so enormous that it keeps the metal in a solid, crystallized state, despite the colossal heat. As if under a giant press, the atoms of iron and nickel are packed with incredible density. Surrounding this solid core is the outer core, a still hot but liquid layer of molten iron and nickel. This is not just a static liquid. It constantly bubbles and flows, like a slowly rotating river of molten metal, creating gigantic convection currents. It is this movement of the liquid outer core that scientists believe generates the Earth's magnetic field, which acts as an invisible shield, protecting our planet from dangerous solar winds and cosmic radiation. Without this shield, life on Earth might be very different, if not impossible. Above the liquid outer core is the most voluminous layer of our planet, the mantle. If you imagine the Earth in a cross-section, the mantle would take up about 84% of its volume. It is not quite a solid, but not quite a liquid substance either, resembling a very thick, slowly flowing resin or plasticine, which is under enormous pressure and at high temperatures. It consists of molten silicate rocks rich in iron and magnesium. In the mantle, there are constant, albeit incredibly slow, movements caused by thermal energy rising from the core. These movements are like giant invisible currents or slowly rotating conveyor belts. Hot rock from the lower layers of the mantle slowly rises upward, cools near the surface, and then, having become denser, falls back down, creating closed convection cycles. It is these slow, powerful flows in the mantle that are the main driving force that shapes and constantly reshapes the appearance of our planet. Without these currents, there would be no movement of continents, and therefore no mountains. And finally, the topmost, thinnest, and most familiar layer is the Earth's crust. Think of it as the thin, fragile shell on the surface of a giant egg. Its thickness varies greatly, from 5 to 10 kilometers beneath the oceans, where it is composed primarily of dense basalt, to 30 to 70 kilometers beneath the continents, where it is composed of lighter but thicker granite rocks. The crust is what we stand on, what we see, what we study, and what we travel over. Despite its apparent hardness and strength, this thin outer shell is not a single whole. It is divided into many giant fragments, like pieces of a huge puzzle, constantly in motion, slowly floating through the viscous but powerful mantle. Like ice flows on the surface of a vast, slow-moving lake, These crustal fragments constantly collide, move apart, and rub against each other, shaping our world, creating the continents and oceans. This constant, invisible movement is the key to understanding how the majestic mountains that we see around us were born and continue to be born. Each layer of the Earth has its own hidden history, its own rhythm, its own contribution to the general, slow dance of the planet. Imagine that the entire crust of the Earth, on which our continents and oceans are located, is not a single whole, and is not firmly attached to the inner layers of the planet. In fact, it is divided into many huge fragments, like giant pieces of some incredible, constantly moving puzzle. We call these fragments lithospheric plates. They are like colossal rafts that slowly, incredibly slowly, drift along the viscous but fluid mantle, which we talked about earlier. Their movement is so leisurely that it is almost imperceptible to us, because it occurs at the speed of our fingernails, just a few centimeters per year. But over millions of years, these seemingly insignificant movements add up to enormous shifts of the continents, completely changing the map of the world as we know it, opening and closing oceans, raising and lowering entire landmasses. What drives these giant plates into such relentless, perpetual motion? The main force behind this great dance is deep inside the Earth and is called mantle convection. This is the process by which heat from the Earth's hot core continually rises up to the surface, while cooler, denser rocks in the mantle sink back down to the core to be heated again. Think of a pot of very thick, slowly simmering soup. The hot part of the liquid rises, cools at the surface, becomes heavier, and sinks back to the bottom to be heated again and begin a new cycle. In the Earth's mantle, this process occurs at an incredibly slow pace, taking millions of years to complete one cycle, but with colossal, almost unimaginable power. These slow up and down currents act like invisible giant conveyor belts that pick up the lithospheric plates located on the surface of the mantle and force them to move in different directions. There are two main types of tectonic plates, and their differences are key to mountain building: oceanic plates and continental plates. Oceanic plates, which form the floors of our oceans, are relatively thinner, usually between 5 and 10 kilometers, and much denser than their continental counterparts. They are made up primarily of heavy rock, such as basalt. Continental plates, by contrast, are much thicker, 30 to 70 kilometers, and less dense. They are made up primarily of lighter granitic rock, and they are what support our continents and most of the land we inhabit. Their differences in density and thickness play a key role in how they interact when they cross paths. Sometimes the plates move apart, allowing the Earth to breathe and create new crust. Sometimes they rub against each other, causing earthquakes. But most often they collide. And it is in these collision zones where gigantic forces compress, crush, and lift the Earth's crust that majestic mountains begin to emerge. It is a long, complex, and incredibly slow process that never stops for a moment and continues to this day, shaping the face of our planet. There are many places on the surface of our planet where the lithospheric plates do not collide in a grand embrace, but instead slowly, almost imperceptibly, begin to move apart. We call these zones divergent boundaries, or boundaries of separation. Imagine the Earth breathing here, slowly but steadily expanding, and in the process creating an entirely new crust. Most often, such amazing geological processes occur deep underwater, at the bottom of huge oceans, where we cannot see them, but can feel their presence through seismic activity and underwater mountains. At the very heart of every major ocean, like a giant seam, stretch long underwater mountain ranges known as mid-ocean ridges. These are the longest mountain systems on our entire planet, stretching for tens of thousands of kilometers under the sea, remaining hidden from our eyes. It is here, along these underwater ridges, that hot, molten rock, magma, slowly but steadily rises from the depths of the earth. It pours onto the surface, hardens under the pressure of the water, and forms entirely new oceanic crust, as if constantly renewing the bottom of our world. This process is like a giant factory that tirelessly, over millions of years, produces new terrestrial matter, pushing it upward. As new crust forms and grows along the ridge, it gradually pushes the old crust aside, causing the lithospheric plates to slowly but steadily move away from each other. For example, the Atlantic Ocean is gradually widening because such a mid-ocean ridge runs right through its center, and the European and North American continents are moving away from each other by a few centimeters each year. This process is like the slow, silent unzipping of a giant zipper on the surface of the planet, through which new material rises. Sometimes, though much less frequently, the continents themselves begin to diverge. The crust is then stretched, cracking and splitting, forming deep depressions called rift valleys. The most dramatic and rapidly developing example of this phenomenon is the East African Rift Valley, which may eventually split the African continent into two separate parts, creating a new ocean in this area. These divergence zones do not usually produce the high, majestic mountain ranges we are accustomed to seeing with sharp peaks. Instead, they create long, low ridges with gentle slopes and deep depressions, demonstrating the other side of the geological process, a process of stretching and tearing, not compression and uplift. But even here, one can feel the colossal, unimaginable power of the moving Earth, which slowly but steadily changes its appearance, creating space for new seas and new lands. It's like a deep, slow breath of the planet, revealing its hidden depths. Imagine a place where two giant tectonic plates are not moving apart, not sliding past each other, but instead moving slowly but inexorably toward each other. We call these zones convergent boundaries, and they are where some of the most dramatic and majestic events in our planet's long history unfold, giving rise to the majestic mountains we see and admire. One of the most common and powerful scenarios for such a collision is an oceanic plate meeting a continental plate. Think of it as two very different tectonic giants, each with its own unique density and thickness. The oceanic plate, while much thinner, is much denser than the massive but lighter continental plate. When these two plates meet face to face, a process begins that geologists call subduction. The word means sinking, and indeed, the denser oceanic plate, like a huge lumbering diver, slowly but steadily sinks down beneath the lighter continental plate. This movement does not happen suddenly, but smoothly and steadily, at a rate of just a few centimeters a year, the same speed at which our fingernails grow. But over millions of years, these centimeters add up to colossal distances, and millions of cubic kilometers of rock are buried deep beneath the surface. As a result of this sinking, the ocean floor, just before the edge of the continent,
is formed by the deepest depressions known as deep-sea trenches. These are the deepest places on the entire surface of our planet, mysterious and hidden from the light, where ocean water disappears into the abyss and the pressure reaches unimaginable levels.
As the oceanic plate sinks deeper and deeper into the hot, viscous mantle, it begins to melt. This does not happen instantly like ice in hot water, but gradually, as the temperature and pressure increase, which build up with every kilometer of submersion. From this molten mass, called magma, huge but very slow-moving bubbles form. These bubbles are lighter than the surrounding denser mantle rocks, and so they begin to rise slowly but steadily, forcing their way up through the thickness of the continental crust. When this magma reaches the Earth's surface, it erupts in the form of volcanoes. But these are not just isolated, scattered mountains. These volcanoes line up in long, majestic chains that run parallel to the edge of the continent from which the plate was subducted. These chains are called volcanic arcs. The most striking and impressive examples of such grandiose mountain systems are the Andes in South America, which stretch along the entire western coast of the continent for thousands of kilometers, or the Cascade Mountains in North America. These mountain ranges are not simply raised by tectonic forces. They literally grew from the depths of the earth, thanks to the fiery breath of the mantle, thanks to the magma that rose from the molten subducting plate. This process of creating mountains through subduction does not stop. It continues to this day, slowly but steadily, forming new peaks, changing the contours of continents, and demonstrating to us the living, ever-changing nature of our planet. It is a mesmerizing dance of fire and stone, taking place in the deepest corners of the earth, which we are now beginning to understand. Sometimes it happens that not a continental plate, but another oceanic plate is denser, and therefore heavier than its neighbor. In this case, one oceanic plate begins to slowly sink under the other oceanic plate. This process, as in the case of a continent, is also called subduction, and it is one of the powerful ways of creating new lands and forming complex geological structures right in the middle of vast oceans. Imagine two huge underwater platforms slowly moving towards each other until one of them begins to slide down, disappearing into the abyss of the mantle, like a giant sea serpent diving into the depths. When the upper oceanic plate begins to bend under the pressure of the subducting plate, deep oceanic trenches form on its surface, just above the subduction zone. These are the same underwater trenches we talked about earlier, but now they form where ocean crust is subducted under other ocean crust, creating the deepest parts of the ocean floor. As the lower, subducting plate sinks deeper and deeper into the hot, viscous mantle, it begins to melt under the intense heat and pressure. This turns the solid rock into molten magma. The resulting magma, being lighter than the surrounding mantle rock, begins to slowly rise upward, pushing through the upper oceanic plate. The result of this massive underwater process is the formation of chains of volcanic islands that line up in long, often curved arcs. These island arcs are essentially underwater mountain ranges whose peaks rise above the ocean surface, forming the archipelagos we see today. The most striking and well-known examples of such formations are the Japanese islands, which arc along the coast of Asia, the Aleutian Islands, which form a bend in the northern part of the Pacific Ocean, or the Mariana Islands, near which the deepest point on our planet,
the Mariana Trench is located. Each volcanic eruption on these islands is just a small but powerful manifestation of the enormous geological forces operating deep beneath the ocean, tirelessly rebuilding the seabed and forming new lands. Such zones are characterized not only by intense volcanic activity, but also by very high seismicity. The subducting plate does not move completely smoothly. It clings to the upper plate, accumulating a huge amount of stress. When this stress becomes too great for the rocks to withstand, a sudden and sharp release of energy occurs in the form of earthquakes. These earthquakes can be very strong, and sometimes they generate tsunamis, giant ocean waves that spread across the surface of the ocean, carrying destructive force. However, even these powerful manifestations of activity are part of the general, incredibly slow and continuous process of planet formation. Through the roar of the waves and the occasional tremors of the Earth, one can hear the quiet whisper of distant underwater mountains that are still growing and changing, following their ancient geological dance, lulling and mesmerizing in its leisurely power.
Of all the types of tectonic plate collisions, the most majestic and impressive mountain ranges are created when two continental giants collide. Imagine two huge, dense landmasses, each carrying entire continents, slowly but inexorably moving toward each other over millions of years. Unlike oceanic plate collisions, where one, the denser one, easily sinks beneath the other, the situation changes dramatically when two continents collide. Continental crust, as we have already discussed, is much thicker and lighter than oceanic crust, like a thick layer of styrofoam. Because of its relatively low density, it simply cannot sink deeply into the viscous mantle. It is too buoyant for that. Instead of the usual subduction, something different happens. As the two continental plates collide, they begin to crumple and deform under enormous, unimaginable pressures that build up over millions of years. It is as if two giant carpets were slowly moving toward each other and began to wrinkle, gathering into tall, massive folds and piles. The rocks that lay at the bottom of the ancient oceans that separated the continents, as well as the rocks of the continental margins themselves, are subjected to incredible compression. They fold into giant curves, slide over each other like layers of butter on a cake, and thicken, forming complex, multi-layered structures that go deep into the Earth's crust, forming the so-called roots of the mountains. This process is slow, stretching out over tens of millions of years, but the results are astounding and create the highest points on our planet. This is how the highest and most famous mountain ranges on our planet were formed, which take our breath away with their grandeur. The most striking and famous example is the Himalayas, which are the result of the ongoing collision of the Indian plate with the Eurasian plate. The Indian plate, which once separated from the ancient supercontinent Gondwana, slowly drifted north, crossing the ocean, and about 50 million years ago slammed into Asia. Since then, this colossal collision has not stopped. India continues to press on Asia, and as a result of this powerful pressure, the Himalayas, including the highest peak in the world, Everest, are still slowly growing a few millimeters each year. This is an active process that is happening right now. Similar processes have created other great mountain ranges, such as the majestic Alps in Europe, formed by the collision of the African and Eurasian plates, or the ancient Ural Mountains dividing Europe and Asia, whose history goes back hundreds of millions of years. These mountains are not just rock formations, they are living witnesses to the incredible power and patience of our planet. They are a powerful reminder that the Earth is not a frozen landscape, not a static mass, but an ever-changing, dynamic system where the forces acting in its depths create magnificent masterpieces on the surface. These peaks of the world, which seem eternal and motionless to us, are in fact the culmination of millions of years of slow but incessant pushing and squeezing. And in their silent grandeur, in their grandiose calm, there is a deep history that can lull any anxiety and give a deep sleep. Beyond the majestic collisions where plates move toward each other and the slow drifts where they move away, there is another, equally significant but often less visible type of interaction between lithospheric plates. This occurs at so-called transform boundaries, where plates do not collide head-on and move apart, but slide past each other, moving in opposite directions or in the same direction but at different speeds. Think of two huge, incredibly massive gears slowly rubbing together, or two giant blocks of ice moving in parallel, creating a furious but largely hidden stress on the Earth's crust. At transform boundaries, unlike the zones where great mountain ranges form, there is usually no significant mountain building. There are no great uplifts or deep subsidences of the Earth's crust that create the majestic peaks and form the mountain ranges we are accustomed to. Instead, the energy of these relentless interactions accumulates as deformations and colossal stresses in the Earth's crust. The plates become stuck relative to each other due to the enormous friction caused by the uneven surfaces of their plates. This stress slowly but steadily increases over many years, decades, and sometimes centuries, turning the Earth's crust into something like a taut string, ready to snap at any moment. When the accumulated stress becomes too great for the rocks to support, there is a sudden and violent release of this stored energy. This instantaneous release is what we call an earthquake. Imagine bending a thick wooden stick slowly and forcefully. It bends, storing up potential energy, and then suddenly, with a loud crack, it snaps, releasing all the stored force. It is exactly like this. Plates that may have been moving millimeters over a year suddenly shift several meters in a matter of seconds or fractions of a minute. These powerful, instantaneous shifts generate seismic waves that travel throughout the Earth, causing the surface shaking that we feel as tremors. The most famous and striking example of such a transform boundary is the famous San Andreas Fault in California, United States of America. Along this fault, the Pacific Plate slowly but steadily slides northwest relative to the North American Plate. This place is known for its frequent earthquakes, which constantly remind us of the incessant movement of the Earth's crust and the colossal energy hidden beneath our feet. However, in the context of our sleep story, even these powerful geological events can be imagined as quiet sighs or gentle shudders of a sleeping planet, which occasionally turns in its sleep, releasing accumulated tension. They are part of its eternal life, evidence that beneath us is not a dead, inert mass, but a living, breathing, constantly shaping world, where even friction gives birth to movement. After the giant lithospheric plates collide and begin to press on each other, or when they stretch and shift, The Earth's crust, no matter how hard it may seem, like pliable clay or plasticine, begins to deform. This happens slowly, over millions of years, under the action of unimaginable colossal forces of compression, tension, or shear. These deformations are not random. They take certain forms, creating complex geological structures that we call folds and faults. They are what make up the internal anatomy of the mountain structure, determining their majestic, sometimes chaotic, but always unique and complex appearance. Imagine that you are slowly but forcefully pushing a thick, heavy carpet across the floor. It does not break immediately, but begins to wrinkle, gathering into gentle or steep waves. In the same way, earth rocks, under enormous, prolonged pressure, do not always break. Instead, they often bend, forming giant, gentle, or steep waves in the thickness of the Earth's crust. These bends are called folds. Those parts of the fold that are bent upward, forming peculiar ridges or arches, are called anticlines. They are often the origin of major mountain ranges and peaks, towering over the surrounding area. And the parts that are bent downward, forming depressions or hollows, are called synclines. River valleys, lakes, or intermountain basins are often located in them. These folds can be of different sizes, from imperceptible microscopic bends that can only be seen under a microscope to huge geological structures visible only from a great height, which extend for hundreds of kilometers, forming entire mountain systems. However, rocks do not always behave in a flexible manner, bending and folding. Sometimes, the stress in the Earth's crust becomes too great and the rocks break apart, forming faults. These are giant cracks or zones of weakness in the Earth's crust, along which blocks of rock slide relative to each other. These displacements can be vertical, horizontal, or a combination of both, and they are the cause of most earthquakes. There are several main types of faults. For example, normal faults occur when one block of rock drops relative to another, creating step-like features on the surface that can be seen as scarps. Thrust faults, on the other hand, occur when one block is pushed or lifted over another, which is very common in compression zones where plates collide, and such faults actively contribute to the formation of mountains. And the parts that are bent downward, forming depressions or hollows, are called synclines. River valleys, lakes, or intermountain basins are often located in them. These folds can be of different sizes, from imperceptible microscopic bends that can only be seen under a microscope to huge geological structures visible only from a great height, which extend for hundreds of kilometers, forming entire mountain systems. However, rocks do not always behave in a flexible manner, bending and folding. Sometimes, the stress in the Earth's crust becomes too great, and the rocks break apart, forming faults. These are giant cracks or zones of weakness in the Earth's crust, along which blocks of rock slide relative to each other. These displacements can be vertical, horizontal, or a combination of both, and they are the cause of most earthquakes. There are several main types of faults. For example, normal faults occur when one block of rock drops relative to another, creating step-like features on the surface that can be seen as scarps. Thrust faults, on the other hand, occur when one block is pushed or lifted over another, which is very common in compression zones where plates collide, and such faults actively contribute to the formation of mountains. And strike slips are horizontal displacements where blocks of rock slide past each other, as we have already seen on transform boundaries,
such as the famous San Andreas Fault.
These folds and faults are not simply static structures left over from ancient cataclysms. They are living scars of the Earth, evidence of its immense power and dynamism and its constant movement. Every fault is a potential source of an earthquake, and every fold is a visible manifestation of billions of tons of pressure exerted over millions of years. These internal deformations, often hidden deep below the surface, determine how mountains look today, how they are eroded by external forces, and how they continue to grow and change slowly but steadily. They demonstrate that even the hardest, seemingly immobile stones obey the invisible but powerful forces of our planet, constantly shaping its unique appearance. And in this slow geological dance, there is a profound harmony that can lull any mind. When we look at mountains, they seem incredibly massive and heavy, standing still on the surface of the Earth. However, imagine that the Earth's crust, no matter how solid it appears, is actually floating on the denser, stickier mantle like a huge iceberg in water. This fundamental principle of geological balance is called isostasy. It states that the weight of mountains and continents is balanced by the buoyant force of the mantle beneath them. The taller and more massive a mountain range, the deeper its root, the denser part of the Earth's crust, goes into the mantle, supporting it, like the underwater part of an iceberg, which is much larger than the part above water. This is similar to how a heavy object placed on the surface of a liquid would push it up, sinking deeper until the buoyant force equals its weight. After the mountains have been raised by powerful tectonic collisions, they begin to be subjected to the relentless action of external forces, the forces of erosion. Wind, water, ice, these great sculptors of nature constantly, slowly, layer by layer, destroy the peaks, carry away rock fragments, and the mountains gradually begin to lose their mass. It would seem that this should lead to their gradual reduction and ultimately to their complete disappearance from the face of the Earth. However, here the amazing principle of isostasy comes into play, which causes an effect called isostatic rebound or isostatic uplift.
As the top layers of mountains are eroded away, their overall weight decreases. Think of a giant iceberg as its top, above-water portion is gradually peeled away. It becomes lighter, and so its underwater portion floats a little, restoring its equilibrium. In the same way, as mountains lose mass through erosion, the crust beneath them becomes lighter and begins to slowly, almost imperceptibly, rise from the mantle, as if the Earth itself were sighing and pushing them upward in relief. This upward movement compensates for some of the destruction, allowing the mountains to maintain their height or even grow slowly, despite the constant erosion that seeks to level them. This process is a kind of geological fitness, where the mountains are constantly training, balancing between the forces that lift them from within the Earth and the forces that destroy them from the outside. This is why ancient mountain ranges like the Ural Mountains in Russia or the Appalachians in North America, which were formed hundreds of millions of years ago and should have completely disappeared under the action of erosion, still exist, although their peaks are no longer as sharp and high as, for example, those of the younger Himalayas or the Andes. Their current shape and height are the result of this continuous, slow dance between tectonic uplift and erosional destruction, between the deep forces of the Earth and the superficial forces of nature. And in this slow but steady process, there is a deep peace that helps us to realize the eternal harmony of our planet, which is constantly in motion and change. As soon as the mighty mountain ranges rise from their depths, The equally mighty but much more patient forces of erosion and weathering immediately take over. These processes work tirelessly for millions upon millions of years, slowly but surely breaking down and shaping even the hardest and seemingly indestructible rocks. Think of the mountains as huge, colossal sculptures, and the wind, water, ice, sunlight, and even living organisms as great, unhurried artists who patiently and persistently give them their final, unique, and ever-changing forms.
Weathering is the first and fundamental stage of rock destruction. It comes in several main forms, each acting in its own way, but always with the goal of preparing the material for transport. Physical weathering works like an invisible hammer and wedge, tirelessly splitting rocks. A striking example is frost weathering. Water seeps into the smallest cracks and pores in the rocks, freezes at night, and, turning into ice, expands, slowly tearing apart the rock from the inside. The heat of the day expands the minerals in the rocks, the cold of the night contracts them, and these constant temperature cycles, repeated thousands and millions of times, weaken the rocks, causing them to crack and flake. Wind, carrying tiny particles of sand and dust, acts like gentle but persistent sandpaper, slowly wearing away the surface of the mountain ranges. In deserts and open spaces, this abrasive effect of the wind forms bizarre rock formations. Then chemical weathering comes into play, changing not just the shape, but the chemistry of the rocks themselves. For example, rainwater, as it passes through the atmosphere and soil, absorbs carbon dioxide and organic acids, becoming a weak solution of carbonic acid. This slightly acidic water can slowly dissolve certain minerals in rocks, especially limestone, creating caves and karst landscapes. It's like sugar dissolving in water, only on a natural scale. It happens over a very, very long time, changing the rock at the molecular level. Chemical weathering can turn hard, stable rocks into soft clays or loose sand, which are then much more easily carried away by subsequent forces. There's also biological weathering, where plant roots penetrate cracks in rocks, widening them, or where microorganisms secrete acids that break down minerals. Once the rocks have been broken down by weathering into smaller particles, erosion comes into play. This is a dynamic process of transporting broken material. Rainwater streams running down slopes pick up particles of soil, sand, and rock, carrying them downhill. Small streams merge into large rivers, which collect these particles and turn into powerful transport arteries. Rivers constantly cut deep gorges and canyons, slowly transporting sediment from the mountains to the plains, lakes, and ultimately to the oceans. Glaciers, which we will discuss in more detail, are like giant, slowly moving ribbons, collecting rock, acting as colossal bulldozers, leveling the landscape and carving out huge valleys. These forces of erosion and weathering are constantly at work, shaping sharp, jagged peaks, gentle, rounded slopes, deep, picturesque valleys, and winding gorges. They slowly but surely wear away the mountains, returning their material back into the great cycle of the earth. Even the mightiest peaks will one day turn to sand and dust, which will become part of new rocks and, perhaps in the distant future, new mountains. This process is endless, and it contains a wonderful sense of calm, the knowledge that everything in nature is in constant but harmonious motion, following ancient, immutable laws. Once mountains have been lifted up by powerful tectonic forces,
and have begun to succumb to the inexorable erosion of weathering, two great architects come into play and shape them in their most dramatic and recognizable ways: glaciers and rivers. These powerful forces of nature, working over millennia and millions of years, tirelessly carve the rock masses to create the magnificent valleys, deep gorges, and dramatic canyons that we see and admire today. Their work is a slow but incredibly effective process of reshaping the Earth's surface. Glaciers, these slow-moving, colossal giants of ice and snow, are incredibly powerful and effective sculptors of the landscape. Imagine a huge, thick, frozen river of ice moving down a mountainside under its own unimaginable weight, gradually sliding downwards. Rocks, debris, and sand freeze within this moving ice, turning the entire glacier into a giant, slow-moving sandpaper or abrasive tool, capable of wearing down and carving away at the hard rock. The glacier doesn't just slide across the surface, it plows out valleys, widening and deepening them, giving them a distinctive, recognizable U-shape, as opposed to the sharper V-shaped river valleys. In addition, glaciers carve out sharp, jagged mountain peaks called carlings or horns, and form deep, picturesque basins that, after the ice melts, turn into clear mountain lakes. In coastal areas where glaciers reach the sea, they carve out majestic fjords, deep, narrow sea inlets with steep, often sheer shores that are true works of art created by ice and water. This slow but inexorable movement of ice leaves an indelible mark, creating a unique, rugged, yet majestic landscape. Rivers, in turn, work like persistent, patient stone carvers. Starting high in the mountains as tiny streams fed by meltwater or rain, they gradually unite, gain strength, and turn into powerful, seething streams. The water carries sand, pebbles, and even larger stones, which, rolling along the bottom and walls of the riverbed, act as an abrasive, constantly eroding and deepening the riverbed. Over time, these rivers cut deep, V-shaped valleys and grandiose canyons, dividing mountain ranges. The speed of their work may seem completely imperceptible on the scale of a human life, but over millions of years, a river is capable of sawing through hundreds of meters of solid rock along its path. For example, the famous Grand Canyon in North America is the colossal result of the tireless work of the Colorado River, which slowly but surely cut its way through layers of rock, exposing billions of years of geological history. Thus, glaciers and rivers, each in their own way, are the key architects of the mountain landscape. They do not simply destroy the mountains, but also give them the complex, picturesque, unique form that we see. They show that nature is a constant process of creation and destruction, in which each element plays its irreplaceable role. And in this slow, incessant dance of water, ice, and stone, there is a deep, lulling harmony that can calm our minds and lead to a deep, serene sleep. Beyond the epic collisions of continents and volcanic eruptions, there is another amazing and less obvious way in which mountains are born. This way of forming mountains is closely connected with the history of ancient oceans and what happened on their floors over countless millions of years. Imagine the vast, endless expanses of water that existed on Earth millions, even hundreds of millions of years ago. At the bottom of these ancient seas, sediments slowly accumulated, layer by layer. These were tiny grains of sand, clay particles, silt, fragments of shells of ancient marine organisms, skeletons of plankton, all that settled from the water column and gradually, over endless time, compacted under the weight of new layers. Over time, these accumulations turned into various types of sedimentary rocks, such as dense sandstones, layered shales, soft limestones made up of the remains of marine life, and even rock salt. These huge accumulations of sedimentary rocks formed powerful, thick layers that we call sedimentary basins, which rested on the bottom of ancient seas. Over time, these ancient oceans would begin to close as a result of the same inexorable but incredibly slow continental drift. This would happen when the two tectonic plates that supported the continents began to move closer together and toward each other. As they moved closer, the vast sedimentary basins between these landmasses would become trapped and subjected to enormous, unimaginable pressure. What had once been soft mud and sand on the seafloor would now be subjected to incredible compression and deformation. Sedimentary rocks that had once been horizontal would begin to crumple into giant folds, pushing against each other as if the earth were literally squeezing them out of the depths. These layers would rise higher and higher above sea level, forming mountain ranges. This is how many of the oldest, and even some of the modern mountain ranges we see today were formed. For example, the famous Ural Mountains in Russia, which run north to south and traditionally divide Europe and Asia, were once the floor of an ancient ocean. Hundreds of millions of years ago, they were uplifted and crushed by the collision of ancient continents, turning seabed into mountain peaks. A similar story is told in the Appalachian Mountains in North America, as well as many ranges in Europe, such as the Jura or parts of the Alps, which include significant sedimentary massifs uplifted from former sea basins. These mountains are thus literally built from material that once lay at the bottom of the sea. These mountain ranges, composed primarily of sedimentary rock, are often more gentle and rounded than the jagged peaks of younger volcanic mountains because they have been eroded for much longer. But they contain invaluable geological records of long-gone oceans, the life that once teemed on their bottoms, attested to by numerous fossils, and the incredible changes our planet has undergone throughout its history. Their silent presence reminds us of the endless cycle of creation and destruction, and how even the deepest sea trench can become the highest mountains. There is a profound sense of peace and infinity in this slow but inexorable process. We've already talked about mountains born from plate collisions and volcanic eruptions, but there are other kinds of mountains whose history begins not on the surface but deep underground, in secret pockets of molten rock. These mountains, called igneous intrusive mountains, form when magma, the hot, molten mass that rises from the mantle, doesn't erupt as a volcano, but slowly solidifies deep within the Earth's crust before ever reaching the surface. Imagine a vast underground cavity that gradually fills with slowly cooling molten rock, which then crystallizes into solid rock. This process takes incredibly long periods of time, millions of years. As the magma rises and cools, it forms massive, deep-seated bodies of igneous rock, such as granite. The largest of these underground formations are called batholiths. A batholith is a giant body of intrusive igneous rock that can stretch hundreds of kilometers long and tens of kilometers wide. They are like the roots of huge, invisible mountains that have not yet emerged to the surface. These underground roots create zones of high strength in the Earth's crust. So, how do these hidden underground massifs become the mountains we can see?
It's through the tireless work of erosion. Once a batholith has hardened into solid rock, millions of years of surface processes, weathering, rivers, and glaciers gradually strip away the top layers of softer surrounding rock. Think of a sculptor slowly peeling away layer after layer of material to reveal his work. Over time, as erosion removes tens of miles of underlying rock, this hard, erosion-resistant batholith is exposed, rising above the surrounding terrain. These exposed granite massifs, which were once deep underground, now form majestic mountain peaks and ridges. A striking example of such mountains are parts of the Sierra Nevada in California, USA, or some ridges in the Rocky Mountains. Their smooth, rounded shapes, often characteristic of granite mountains, are the result of the long-term effects of erosion, which has polished their surfaces over millions of years. These mountains did not spew lava and ash. Their birth was quiet and slow, taking place in the depths. They tell us a story about the patience of the earth, how even the most hidden processes in its depths eventually manifest on the surface, creating landscapes that inspire us with awe. It is another reminder that the Earth is a complex, multi-layered organism where each element plays its part in the eternal dance of creation. Deep within the Earth, where extreme conditions prevail, rocks can undergo amazing transformations, changing their structure and composition. This process is called metamorphism, and it gives rise to metamorphic mountains. Imagine that existing rocks, whether sedimentary rocks formed at the bottom of ancient seas or igneous rocks solidified from a melt, are subjected to enormous pressure and high temperatures, but do not completely melt. It is similar to how clay turns into a solid brick under enormous pressure and heat. These extreme conditions occur in several scenarios. Most commonly, they occur in areas where lithospheric plates collide, where huge masses of rock are crushed and pushed to great depths. Here, the pressure from the accumulating layers and the heat from the mantle act on the rocks, causing their minerals to recrystallize and their structure to change. For example, ordinary sandstone, rich in quartz, can be transformed into dense, hard quartzite. Soft limestone, made up of ancient shells, can be transformed into the sparkling marble we value so much for its beauty. And clay shales can be transformed into gneisses, banded, highly metamorphosed rocks often found in the cores of mountain ranges. These metamorphic rocks are often extremely hard and resistant to erosion, allowing them to form the strongest and most durable parts of mountain systems. When these deep layers are exposed at the surface by erosion or further tectonic uplift, they form the cores of majestic mountain ranges. Their distinctive layering, sometimes bizarre patterns, and altered crystals tell the story of the incredible pressure and heat they have endured. Metamorphic mountains are witnesses to the deepest and most intense mountain building processes. They show us how the Earth can literally reforge its materials, creating new, stronger structures from old ones. It is these rocks that often form the foundations of ancient mountain shields and continental cores, demonstrating the planet's amazing ability to renew itself and transform itself. Their quiet grandeur hides a history not only of destruction, but also of rebirth, reminding us of the eternal strength and energy of the Earth, which slowly but relentlessly changes its appearance. Their stability and strength
are a reflection of the deep peace that can be found in understanding the scale of geological time.
When we think of volcanoes, we often conjure up images of tall, smoking cones spewing lava and ash. And indeed, volcanism is one of the most spectacular and dramatic forms of mountain building. However, its role in shaping the landscape and creating mountains is much broader and more varied than just the erection of individual cones. Volcanism is a direct manifestation of the Earth's fiery breath, its way of releasing heat and material from its depths. There are different types of volcanic mountains, each formed differently, depending on the composition of the magma erupting and the nature of the eruptions. Stratovolcanoes, or composite volcanoes, are the classic conical mountains we see on postcards. Fujiyama in Japan, Vesuvius in Italy, Etna in Sicily. They form from alternating layers of viscous lava, ash, pumice, and rock debris. Their eruptions can be explosive and dangerous, as the viscous magma seals the vent, building up enormous pressure before escaping. Another type is shield volcanoes, such as Mauna Loa in Hawaii. They have very gentle slopes and are enormous in size, resembling a shield lying on the ground. These volcanoes are formed from very fluid lava that flows relatively calmly and spreads over large distances, gradually increasing in volume. Their eruptions are usually less explosive, but can continue for a very long time, creating massive basalt plateaus and vast volcanic islands. But volcanism is not just bottom-up mountain building. It is closely linked to global tectonic processes. Most of the world's volcanoes are concentrated along the subduction zones we've already discussed. When an oceanic plate subducts beneath another plate, it melts, and the resulting magma rises to form volcanic arcs, long chains of volcanoes, whether on continents like the Andes or in oceans, island arcs like the Japanese islands. These chains are huge mountain systems created by volcanic activity. Volcanism can also be associated with hotspots, places where stationary columns of hot rock, plumes, rise from deep within the mantle, melting the crust regardless of plate boundaries. The Hawaiian Islands are a prime example of such a chain of volcanoes, with each island being the trace of a plate slowly moving over a stationary hotspot. The long-term impact of volcanic activity on landscape formation is enormous. Eruptions not only create new mountains, but also enrich the soil, change the climate, create new minerals, and form unique ecosystems. In their quiet but powerful breathing, volcanoes remind us of the living, fiery essence of our planet, which is constantly reshaping itself, and this constant movement can be surprisingly soothing. We are nearing the end of our immersion into the history of mountains, and now is the time for deep reflection. When we look at the majestic mountain ranges, they seem absolutely motionless, eternal, unaffected by the passage of time. But this, as we have already understood, is only an illusion created by our short human perception of time. In fact, mountains, like everything on our planet, go through their own unique life cycle. They are born from the bowels of the earth, slowly grow, reach their highest point of greatness, and then, just as slowly but steadily, are destroyed by external forces. It is an endless process of cyclicality and rebirth, controlled by the enormous, invisible forces of our planet. Understanding this continuous cycle requires us to rethink our perception of time. We need to delve into the concept of geological time, the scale of which is simply staggering.
Imagine that the entire history of the Earth, from its inception and formation to the present day, is compressed into a single day. On this colossal scale, human civilization, with all its wars, discoveries, and achievements, exists only in the last few seconds before midnight. The life of mountains is measured not in hundreds or thousands of years like human generations, but in millions and even hundreds of millions of years. This is a period of time that is impossible for our consciousness to fully grasp. But it is in this period that the true grandeur of geological processes is revealed.
The mountains we see today are just a snapshot, or, if you prefer, a single frame in this continuous, endless stream of geological time. The Alps and the Himalayas, for example, are considered relatively young mountain systems. They are only a few tens of millions of years old, and they are still slowly growing under the influence of incessant tectonic pressure. Whereas the Ural Mountains in Russia or the Appalachians in North America are ancient, old mountains. Their age is measured in hundreds of millions of years. They are already heavily eroded. Their peaks are smoothed and rounded, but they continue to rise slowly due to isostasy, maintaining their existence in an eternal dance with nature. Their presence is an echo of long-gone eras. This eternal cycle means that the material that makes up the mountains is constantly being recycled and renewed. The broken-down particles are carried away by wind, water, and glaciers, settle on the ocean floor, compact, and turn into new sedimentary rocks. These rocks, after millions of years, can be raised again from the depths of the sea by new tectonic collisions to form new mountain ranges, thus closing the cycle. It is the endless circulation of matter and energy that makes our planet truly alive and ever-changing. The awareness of this cyclicality, this slow, unceasing movement, can bring a deep sense of peace and tranquility. For if even giants like mountains follow this cosmic rhythm, then our own lives are part of something much greater, eternal and harmonious. And in this understanding lies peace. While the deep forces of the earth tirelessly shape and reshape mountains, external factors, the atmosphere and climate, play an equally important role in sculpting them into the final form we see. Think of climate as more than just weather, but as a long-term, stable system that dictates which erosive forces will dominate a region and how quickly the mountain landscape will change. These atmospheric processes act on the surface, changing the mountains layer by layer, day by day, over millions of years. Temperature, for example, plays a key role. Sharp changes between daytime heat and nighttime cold cause rocks to expand and contract, gradually destroying them. In high-temperature conditions, intense chemical weathering occurs, accelerating the disintegration of minerals. In cold regions, especially in the highlands, where temperatures often drop below zero, frost weathering dominates. Water, penetrating into the cracks of rocks and freezing, expands, acting as a wedge that slowly but inexorably splits the rocks. This is why high, rocky peaks often have sharp, jagged ridges, the result of intense frost weathering. Precipitation, be it rain or snow, are powerful agents of erosion. Rainwater running down slopes collects in streams and rivers, which cut deep gorges and valleys. The more abundant the precipitation, the more active this process is. Rivers saturated with rock debris become powerful natural abrasives, capable of cutting through even the hardest rocks,
forming V-shaped valleys and canyons, as we have already said. Snowfalls and the subsequent accumulation of snow that forms glaciers lead to a completely different type of erosion, creating characteristic U-shaped valleys, carlings, and fjords. This is why mountain landscapes subjected to ancient glaciation look different from those dominated by water flows. Wind also contributes, especially in arid regions or on exposed treeless peaks. Winds carrying sand and dust act as an abrasive, polishing rock surfaces to create strange shapes, arches, and outliers. Wind erosion also plays a role in transporting small particles that can then settle elsewhere, forming new sedimentary deposits. Climate and atmosphere, then, do more than simply influence the weather. They are active sculptors of the mountain landscape. Climate change, such as the advancing and retreating ice ages, radically alters the pace and nature of erosion, transforming the appearance of mountains over geological time. Mountains and climate are in constant interaction. Mountains influence precipitation, creating rain shadows and unique microclimates, and climate, in turn, shapes their appearance. It is a complex but wonderfully harmonious interplay of all Earth systems that constantly rebuilds and renews the face of our planet, creating an endless variety of forms and landscapes. And in this slow but relentless process, one can find a profound sense of peace.
We have looked at how the Earth's deep forces and atmospheric processes shape mountains. But there is another amazing artist on this grand canvas of the Earth, the biosphere, the sum of all life on our planet. Life, seemingly so fragile, plays a much more significant role in shaping the mountain landscape than it might seem at first glance. Mountains, in turn, create unique conditions that determine the diversity and adaptation of life. Firstly, the mountains themselves are huge ecological niches. Due to the sharp changes in altitude, temperature, pressure, and humidity, they create many different climate zones over a relatively short distance. Warm valleys can stretch at the foot of the mountains, and eternal ice and snow can be found at the tops. This leads to amazing biodiversity. Each altitude zone has its own unique species of plants and animals adapted to certain conditions. High mountain forests, alpine meadows, tundra on the tops, all this is the result of the interaction of mountain relief with climate, created by these stone giants. Mountains act as natural barriers, contributing to the isolation of species and the formation of new, unique ecosystems. Secondly, life actively participates in the processes of weathering and erosion that we have already discussed. This process is called biological weathering. The roots of trees and shrubs, penetrating the smallest cracks in the rocks, can grow and gradually widen these cracks, literally tearing the stone apart. Lichens and mosses, settling on exposed rocks, secrete weak organic acids that chemically destroy the surface of the stone, preparing it for further erosion. Dead plants and animals enrich the soil, making it more fertile and promoting the growth of new vegetation, which, in turn, stabilizes the slopes, preventing landslides and accelerated erosion. Thirdly, vegetation plays a key role in stabilizing mountain slopes. Dense forest cover or grass carpet holds soil and small rock fragments, preventing them from being washed away by rain and slowing down the development of landslides. Deforestation in the mountains, on the contrary, often leads to increased erosion and catastrophic mud flows. Thus, the biosphere acts as a kind of living glue that holds mountain surfaces together and slows down their destruction. The influence of the biosphere on the mountains, though less dramatic than tectonic shifts or volcanic eruptions, is constant and pervasive. Mountains create the conditions for life, and life, in turn, slowly but surely shapes and changes the face of the mountains. This is further proof that our planet is a single, interconnected system, in which every element, from the core to the smallest plant on the mountainside, participates in the great, never-ending dance of creation and change. And in this endless harmony between stone and life lies a deep, soothing calm. We have come to the end of our slow but profound journey through the vastness of geological time. We began with a sense of eternity and stillness in the mountains, and now we understand that they are dynamic, living witnesses and participants in the endless dance of our planet. From the first invisible movements in its red-hot mantle, through the grandiose collisions of continents, the rises from the depths of the sea, and the fiery eruptions of volcanoes, to the tireless, patient work of wind, water, ice, and even living organisms. Each stage of this process was part of a single, majestic cycle. The mountains that seemed static and eternal to us turned out to be constantly changing creatures, a living chronicle of the earth, frozen in stone, but constantly rebuilding itself. Now, as you sink into deep rest, imagine these sleeping giants. Their jagged or rounded tops silently reach toward distant stars, their mighty roots reaching deep into the very bowels of the earth, where magma is born and plates move. They stand there as if meditating for millennia, watching the seasons, the lives of men, the bustle that unfolds at their feet. Their calm is infectious. It reminds us that there are forces in the world far older, more powerful, and more patient than our daily cares and fleeting worries. It can bring a profound sense of peace to realize that these colossal landscape forms are the result of such long, slow processes, stretching over millions and billions of years. Our own worries and anxieties seem so small, so fleeting, against the backdrop of this geological time, this endless rhythm of creation and destruction. Feel yourself part of something much larger, part of this endless cycle, where everything is born, changes, and is reborn, following the ancient laws of the universe. Let the image of the mountains, their slow breathing, their ancient whispers, and their serene presence accompany you in your dreams. Let their serenity envelop you, their eternal energy calm your mind, their stability give you a sense of security. We have only had a brief moment in their long history, but it is enough to feel their deep peace and wisdom. Now, let go of all remaining thoughts. Your journey is complete. Let this ancient, lulling wisdom of the mountains rock you into the deepest, most restful sleep. Good night.